that. And I don't think I need to share my screen yet. I have your homework up. That way, in case you refer to question numbers, I can help you. But does anyone want to ask specific questions about homework? Either how to make variables, set up the models, answer questions, etc. Yes, I don't know how to call on people. Yeah, Jing, you want to ask? I think I saw your hand up. Okay. Okay. Expand the model to allow a separate moderation effect. Yeah, I'll go ahead and share the screen. That way you can look at it with me. Why not? Separate moderation effect of experience on training type as a separate predictor of each outcome. So that is my way of saying I want 4 interaction terms because I want to allow each group to have their own effective experience, and I want that effect for each group to be different across the 2 outcomes. So it's 4 effects of experience altogether. How they get entered into the model depends on how you decided to set it up. If you went with the approach, here, let me open up something and start typing. That might make it easier to keep track of what I'm talking about. Get a Word document going here. Okay, so if you did, what I'm expecting is that you may have something like in your data set, like you have the dummy code variables would be like DVP and DVC or something like that. So you would have something like model. If you're following like my own notation, you can do it however you want, of course. You would have like DV for the pancakes, DV for the crepes. And so that means if you have those 2 in there, those are your dummy codes, so you don't have a general intercept. And then you would have the effect of group. And so it'd be like group of pancakes versus crepes. And then DVC times group for pancakes versus crepes, something like that. So that would get you into section 1 would just be this much. Section 2 adds these 2. So is everybody okay, at least with those 2 sections? So it's the experience part, right? Okay. So if you're in this coding scheme, then the effect of DVP is the intercept for the P group, right? When predicting, I'll just say making, since that's how the questions are worded, right? So that's what DVP means in the model. So take the effect of. Likewise, DVC would be the intercept for the P group still, but when making crepes. And then we've got the 2, they're not interaction terms, they're actually main effects. But this describes the difference in their pancakes, can't spell pancakes, between pancake group and crepe group, like that. And that means this one would be the difference in the crepes between the P group and the C group. So this is the way that I set it up, where that the group variable is constant. You may also have set it up so that it's the trained versus untrained. I think, Jeff, the code you sent me, you did it that way, since that's the way the questions are worded. So it would be like whichever is the reference is the one that it's like that's the one they got trained in or the one they didn't get trained in. You may have set it up that way. But if you want to allow the effective experience to differ across outcomes, right, then you need to add DVP times experience, centered at whatever, and DVC times experience, centered at whatever. So that would give you the effective experience in making pancakes, the effective experience in making crepes, but they're conditional on the interaction. That would just be for each group. So that would be, I'll say this here, effect of experience when making pancakes. Pancakes, there we go. Effect of experience when making crepes. But that's not what I asked for, right? Because this presupposes that the effective experience is the same no matter which you were trained in. So I got to fix it. So I'm going to do that times, there, I'll do it, put it first since it keeps the format the same. Group P versus C times experience. And group P versus C times experience. So then this is how the effective, let me start the start of the sentence here. How the effect of experience when making pancakes differs for C versus P group. Or nope, other way around, P versus C. And then this one, how the effective experience when making crepes differs for P group versus C group. So it's 4 terms altogether. And so then once you add these two, this is not just the effective experience when making pancakes, it's when making pancakes and trained in pancakes. And this is and trained in pancakes as the reference group. So what these terms mean is entirely dependent on how you set it up. This is one example of what it would look like. Okay, Lexi, go. Um, so this is section 1. Add these for section 2. And then you need all 3 of these added for section 3. So that means that depending on how you set it up, some of the effects of experience are given directly by the model and some of them are linear combinations. Okay, so those of you who had questions about this, does this help or do you want to talk about it more or using a different setup? Say the last part again, as the exact for the crepes? Uh, yeah, so so if you want to know what the effective experience is in the crepe group when making pancakes, it's that one plus that one. Yeah, and the effective experience in the crepe group when making crepes is that one plus that one. It is. It's only 4 means and 4 slopes, but it's very complicated. It's kind of fun though. So the only actual interaction terms in this model are the last 2. This is an interaction of group by experience for each DV. Everything else is either an intercept or a main effect. Sure. Any other homework questions I can help you with? Hmm. Yes. So let me. Yeah. No, it's okay. This is good. This is the reality of how to fight with software to make it do what you want, which is like I'd say 80% of the battle in learning statistics is trying to figure this out. So let me do your model, okay? So if you did the class and you had person in here and you had DV, but you also put group B versus C like that. Okay. So everything up to this point, it understands that because you have each of these intercepts, that you only need one of the two internal contrasts here. But if you left these out, here, let me do the font thingy for them. Like if those weren't there, then because there's no reference, like comparison for what the effective experience should be, it's going to give you two. It's going to give you one for each of the internal codes. So the same thing would happen here. If you left these out, then that one thing would generate a line for the P group and the C group, and it would be what the intercept is in each group. And then this would be what the intercept is in each group. Like this would give you four means. And then the same thing, this gives you two slopes and this gives you two slopes. Hmm. So your model is equivalent. Hmm. So one thing to keep in mind is that if you've got sort of a half and half model right now, then like these are going to be phrased as differences, but these aren't. So that will make it a little bit more challenging to keep track of. I would try to make it symmetric. I would either get rid of these so that you've got the four means given to you by this two numbers, or add these in so that they're parallel. Then watch out for what it does to your grouping variable because the highest one is the reference. So it's going to make it backwards. Uh, it's not, if you're going to use estimate statements to do everything, then it doesn't matter because every time that you see this group in your code somewhere, like estimate, something for group, you would have to put a 0 and a 1. Like you'd have to say which group it is, and those are in the right order. So it's only in the solution that it gives you potentially that differences are backwards because the one group is the highest and the one is the new 0. And that's confusing as hell. So that's why I generally don't put dummy coded things on the class statement. But it's not necessarily wrong to do so. But as long as you get the right, like you put the zeros and ones, I want it for this group and this outcome, like then you'll be okay. Sure. All right, others. Free homework help. I'm feeling generous today. I just heard that we're doing student evaluations after all, and I'm hoping to bribe all of you. Even though they promised that they weren't going to be used in our merit evaluations. Which is sort of hilarious because, the university is going to run out of money and we're not going to get raises like ever again. So I'm not sure what good it does to be meritorious, but but I'm still going to keep trying. All right, well, let me know if you run into other problems setting this up. Otherwise, we're ready to move on. We have a new lecture to do today, maybe to do Thursday as well. Let me make that go. Here we go. Introduction to Multivariate Generalized Linear Models is what I've got here, lecture 5. Feel like doing this? Yeah. Well, you came, right? So, I mean, you must have felt like doing something. This is a lot of this is just conceptual stuff. So the big picture is that I have to try and explain to you how to put in residual correlations between residuals from the same person or sampling unit when there is no such thing as residual variance. That's the big picture. How do you trick the model into doing that? And the way that you do it is through a random intercept. So you can either just accept that, and I'll show you like the way you can accept it, or if you want to understand what the hell a random intercept is, then I felt compelled to explain that to you as well. So that's my lead in. This is a brand new lecture that I've sort of pulled together across different classes. Those of you who had multi-level with me, this will sound familiar. And those of you who haven't yet, well, then you get to have a preview here. So let me make this big. There we go. All right, multivariate dependency. So back to the big picture here. We're talking about general and generalized linear models this semester, where the thing that makes generalized models different is the use of a link function. So whenever you have an outcome that is bounded in particular, you have to do something to the predicted mean that tells the model to obey those boundaries. So for instance, if you're predicting a binary or categorical outcome, then we have boundaries of 0 or 1. We use a logit link to make sure that the predicted outcomes, the probabilities, stay within that 0 or 1 thing when you unlogit them via an inverse link. We have a linear predictor is what it's called, same as usual, this whatever combination of fixed effects that you want to have that allows for effects of your predictors. And then we had a series of conditional distributions. Given the possible values of the outcome, like do they take on values from only 0 to positive? Do they go all the way along the number line? Are they discrete? Are they continuous? Based on what kind of outcome you have, you can figure out what sort of conditional distribution makes the most sense. And so we looked at, say, Bernoulli, multinomial, the Poisson negative binomial family, gamma, um, binomial, and beta binomial, and all that stuff. So there's a whole bunch of those. So all of this is well and good. And when you only have a univariate outcome to predict, it's fairly straightforward. The question is, how do you translate all of this stuff into multivariate space? And it turns out that's actually a lot harder. How do we expand the model for the variance to allow covariance between the outcomes that come from the same person? So I'm saying sampling unit sort of in general, but it could be like the same family or the same person, whatever unit has been sampled multivariately. How do we do that? So we can, just to remind you, there are two ways of going about estimating these models. One is by tricking univariate software. And so that's what you've seen so far is we stack the data so that all the outcomes are in one column. We build dummy codes to keep track of which DV is which, and we put them in the model to act like switches so that we can tell it to predict, use these predictors for this outcome and use those predictors for this other outcome. So that works well in situations in which the mean differences between the outcomes are of interest, different scores are of interest, or you care about the differences in effects of predictors. In all of those situations, what we've done so far will work just fine. You can build in correlations directly or indirectly by telling it what kind of R matrix you want to have. We saw examples of that. When you need to have outcomes that predict each other, so if an outcome is both a predictor and an outcome at the same time, then you can't use the univariate software. We can't just stack it into one thing and call it good. That's when we move to path models. And in that case, we can still build in our relationships between the outcomes from the same person directly or indirectly, but the difference and what's available to us depends on what kind of outcome it is. So here's sort of my attempt at giving you a framework for what is available to you based on what kind of model you're fitting. So the big picture dependency. If you have more than one outcome from the same sampling unit, we have to find a way to tell the model that the outcomes from the same whatever are correlated. That's what we have to be able to do. How we can do it, though, depends on whether or not it's a general model or a generalized model. So what we've talked about so far, this is slide 4, is when you have a balanced design, meaning that the same possible outcomes, the same set of possible outcomes are available for each sampling unit. So like I have DV A and B, the end, or I have pretest, post-test, the end. When you're in that situation, and all the examples we've seen so far of multivariate models were using a normal distribution, then you can just put in an R pattern. And so this is what we've done so far. It's just this little part of this little cell. If you're not in this, if you have a multivariate set of outcomes that each need a generalized model, or at least one of them does, or if you're in the situation of having an unbalanced design, you can't just throw in a residual correlation and call it good. You have to do something else. And that something else is random effects. And so there are letters that go along with the various matrices that make this machinery work. These are the letters that show up in documentation for these models, and so I'm trying to use them to be consistent. What you've seen so far is the R matrix. Today you're going to meet the other friends, G and V. V is what happens when you put G and R together. Welcome to the jungle, everybody. Yes, thank you for getting that joke, people in my age cohort. We got fun and games. We got everything you want. G and R. So this is what we have. This is where we're going. So just to review where we've been. If we have a multivariate model and all of the outcomes can be described with normal residuals, easiest thing to do is tell the software what kind of R matrix we're going to have. So the R matrix is the variance covariance matrix of the residuals, where you have dimensions of the matrix equal to the number of outcomes. So if you have 2 outcomes in the same model, it's a 2 by 2 R matrix. If you have 3, it's 3 by 3. Each person in theory has their own, so that one person's can be 2 by 2 if they don't have all 3 outcomes, for instance. But the way that it gets built is using the same parameters that everybody shares. So let's say that I have a 3 by 3 matrix. I have 3 potential variances, 1 for each outcome, and I have 3 potential covariances. And so there are choices as to what pattern those variances and covariances should take on. If you just want to let them be whatever they want, that's a good strategy if you don't have that many. That's known as unstructured. So in that case, each outcome gets a separate residual variance. There's no constraints, and each pair of outcomes gets a separate covariance. So you just have 6 parameters. You'd say, okay, let the variances be whatever, let the covariances be whatever. The other 2 that are on here are ways to save parameters, and they become more important to consider when you have a lot of outcomes at the same time. So compound symmetry heterogeneous is a compromise with respect to the covariances. It constrains all of the covariances to be caused by a single correlation, so it saves on the number to be estimated, but it still allows each outcome to have its own residual variance. Stata doesn't have that one. The last one here on the list is compound symmetry, and that is to try and save on both covariances and variances. It constrains all of the variances to be the same across outcomes and all the covariances to be the same. There are like 30,000 other kinds, but they are more relevant for R matrices that have to do with either spatial dependency or temporal dependency. So these are kind of the generic dependency ones that you would have available to you. So we're focusing on this compound symmetry one today here, because this is the one that we have to try to recreate in generalized multivariate models. So the compound symmetry, or CS, can be set up equivalently a different way that involves two matrices. So we're going to take R and split it into G and R, which are separate things. And this is the strategy that you have to use. Go back to the previous slide here. If you have multivariate generalized models, or if you have any kind of unbalanced design where not everybody has the same possible set of outcomes. So this is what compound symmetry looks like. I'm on slide 6 at the top here. It says that each outcome is a combination of what is common, so variance that's in common across outcomes, plus variance that's specific to that outcome. E variance is known as residual variance in this context, and it says that the part that's in common is responsible for the covariances. That CS thing is the same thing as what we're going to call by the end of this random intercept variance. U0 is a random intercept. I'm using tau as the symbol for the variance, tau squared, following every other set of notation on the topic that I'm familiar with. And so the way that this random intercept variance thing is going to get used is shown down here. So if you take this random intercept variance and combine it with the R matrix that looks like this, where we have each outcome has a separate, or excuse me, has the same variance and there's no covariances, you get this thing that's called V right here, which has the same exact pattern as R up above. So what it looks like is that I'm just literally switching out notation. CS is the same thing as random intercept variance. And I'm describing how these matrices get put together with quotes, like these are air quotes, because if you know anything about matrix addition, you know that this is not possible the way I wrote it. But conceptually, if you think about this random intercept variance, this one number, if you take that thing that's over here in some place called G and you stick it everywhere in this R matrix, that works out to be the V matrix here. Okay, so to some of you, this may be sufficient. Just simply saying, oh, well, the compound symmetry thing that we had before, that parameter, is now just going to be captured by a random intercept, and that's what we're going to put in our models instead if they're generalized. But that begs the question, what the hell is a U? And how can I have a variance of them? We haven't met U yet. Not U, but U, the letter, right? We've only had E's. So let me go back, way back, and explain where this U idea comes from and what it means conceptually, and why it works out that this combination right here is able to do the same thing as compound symmetry, and what that does and doesn't mean in terms of flexibility. So let's go back. And every time I wrote this, I had the Aretha Franklin song in my head for Think. Do you know that song? Yes, like, let's go back, let's go back, let's go way on, way back when. That one, that's the letter here. We're going way back when. Back to an empty model where there's no predictors and we're pretending everything is normal, just for a little bit here. If I know nothing else about a person, my best guess for their outcome is their mean, right? That's what the intercept is going to become. In this set of data right here, the mean is at 90. So if I wanted to predict what this person out here, their best guess is still 90, because that's the mean, but we're off by 58. That's their residual. If we take the set of these residuals and find their variance, then that thing is residual variance. And so at this point, if you have no predictors, your residual variance of the E's is all the variance that there is to be had. But if we change the setup from a univariate, each person has one outcome, to let's say that embedded inside this picture, each person actually has 5 outcomes. So this is what it would look like for 3 people. I have a blue person, a yellow person, and a purple person. Now, how does that idea of an empty model change? Well, if I'm going to predict the outcome for each outcome for each person, I could start off with just the mean across all the outcomes as my best guess. That is the grand mean, beta. Now I'm going 0, 0 here because I have an index for which person and which outcome. And the E takes on the same IT index for which person and which outcome, where T is for outcomes. That's my fixed intercept. I've said fixed effects throughout the semester, not because I needed to, but because of habit. Because there's another kind of effect that's out there, and that's a random effect, and that's what you're going to meet today. This empty model, this best naive guess, where I give each person the grand mean, I don't have to give a naive guess, because in addition to knowing what the grand mean is, I also know from which person a given outcome came. So if I build in that information to make a prediction to be person specific, if I start off with a best guess that's not the grand mean, but each person's own mean, that's going to form the basis of what's known as a random intercept. So the fixed intercept, everybody gets the same. It's a constant. Everybody shares it. The random intercept is something where everybody's going to get their own. So what's going to happen is that we're going to split the variation in an outcome into two sources. One of it is going to be the difference of the person means. So the blue person here is higher on average than my yellow person, and my yellow person is higher than my purple person. Why is that? Well, I don't know. I just know that they are. So that source of information is what's known as between person variance. It's cross-sectional differences in the mean. So it's why is one person higher than another, or inter-individual differences. The other source of variance then that I'm left with is within person variance, and that's the difference between each person's mean and each of their outcomes. And that's known as intra-individual differences, and that's the part that's only observable in multivariate data. Longitudinal data here, if we think of these as 5 occasions, for instance. So this is the jumping off point in multivariate models where you're trying to think about how much of the outcome variance is because of the person who was sampled versus the outcome that was sampled. So let's say that I have longitudinal data as a specific case of multivariate data where I have 5 occasions. And let's say that the mean across time is given by this black line, and these are individual data points for a red person, orange person, and so forth. If I were to think about error in a univariate way, that would be the difference of the sample mean from each person's observation. So this would be an empty model, sort of in a univariate context, where E is all the reasons why this person is different at each occasion from the sample mean. So I've got an E at time 1, time 2, time 3, time 4, time 5. Now these E's are related to each other. They're all negative. And that's because this purple person is lower on average than other people. So what if we change the way we're thinking about error variance to explicitly take that person's mean difference into account? Well, then we end up with our new letter. So this is slide 13. Let me introduce you to U. U is a random intercept. If we take each person and give them their own mean, so that's this dotted line through time right here, U for that person is the difference between the sample mean and their person mean. So U is trying to capture what is common to a person across all of their multivariate observations. Because this person is lower, their U would be negative. Somebody who is above the mean all the time, their U would be positive. But each person gets their own U. And they share their U across all of their observations for outcomes in the model. From there, the E is how far off your outcome still is from that person mean. So E in this context is outcome-specific variance. It's been sort of purified or controlled for the person variability, and it's just the variance that happens at each occasion, or for each outcome in a multivariate context more generally. In other words, this random intercept represents a source of dependency of a particular form. It says that the only reason that the outcomes from the same person would be correlated is because of some kind of constant person mean difference. And once you adjust for that, once you take that person difference and give it a variance in the model, what's left, these E's, have the regular, independent, and equally distributed assumptions in a regression linear model. So putting it together, what this is trying to do is take all of the variability in one column, so all the people, all the different outcomes, and say that it comes from two different sources. U variance, this random intercept variance, is the difference between the person means, and the E variance, which is going to be called residual variance, is the remaining differences of each person outcome from their mean. So if you put it together, we've changed sort of the baseline empty model in a univariate to a multivariate context by adding in this random intercept. So in a univariate context, we would say that the empty model starts with just the mean for the outcome plus how far off any observation is from the mean. A multivariate empty model would have a mean noted that you usually allow a different mean for each outcome outside of longitudinal data. Longitudinal is kind of a special case where you tend not to do that. But the total variability is now segmented into how much of it is because of you being above the mean all the time or below the mean all of the time. And then from there, E is what's left. How does your outcome at this particular occasion compare to your mean? So in theory, the total variability is the same. It's just been partitioned into two sources. What is due to a between-person random intercept and what is due to a within-person residual. Okay, so a lot of concepts. How are we doing so far? Okay. Yellow thumbs up. I like it. So if we try to talk about how to characterize one person's set of observations, we have a slightly different setup than what you've seen before, but it works out to be the exact same thing as a compound symmetry model. So let's say that we have an empty model that has three outcomes. And I see a typo in here that I'm going to need to fix. This one should be DVB right here, beta 0. Beta 0, 2 attached to that. I'll fix that later. Let me make sure, yeah, still streaming. That's good. Okay, so we have the outcomes for one person. So here's three outcomes for that person. We have the X matrix before. That holds all of the predictors that have fixed effects. That is also known as a design matrix in sort of classical design of experiments literature. And then we have our beta matrix that holds the fixed effects themselves. Here's the new part. Our new friends Z and U. Z is a matrix that holds predictors. It's the predictors that have random effects. And in this context, it's only an intercept. What a random effect is a parameter that each person has their own of. And so the random effects themselves are in the U matrix. So beta 0, 0, for instance, is shared by everybody. That's my fixed intercept. UI0 is the random intercept, which is how far off each person's actual intercept is from the one for the sample. So these are individual variables in here that have to be estimated. They're not, let me start it again. They are unknown quantities. And just like E is an unknown quantity, and we don't know what U is until after we fit the model. So the model for the total variability in the outcomes is going to be a combination of this part in blue here, the U and the E. What ends up happening is that the U and the E get put back together again in this form right here. So G and R together make V. V is the total combined variance and covariance matrix across outcomes. It has a between person part, which is this ZGZ transpose part, and a within person part, which is the residual variance in R. So the Z and the Z transpose just serve to make it so that we can actually add these two matrices together. It makes it into the same, the right dimensions. And then when you work through the math, you end up with this form right here for V, which is exactly the same thing as what we used to call compound symmetry. So that compound symmetry pattern is perfectly and equally recreated by this approach by putting in a random intercept whose variance is estimated in a place called G, and then combining that with E variance that remains in R. So when you put the two back together again, you get this thing called V. And this approach generalizes to unbalanced designs for general linear model type analyses. Multivariate general linear models that have unbalanced designs or balanced designs can be addressed this way. And you can have other things inside your Z and U matrix. You can actually have random slopes. So if you have a predictor that is measured at each outcome or for each outcome, like if you have your outcomes are occasions, you might have an outcome variable at each occasion and a predictor variable at each occasion. You can estimate a random slope also for that predictor that allows each person to have their own slope, and that would go into here as well. So that's the world of multi-level models or mixed effects models that include both intercepts and slopes. We're not doing that right now. We're just going to stick with the random intercept. That's a way that we can get the same sort of pattern as a compound symmetry approach. It's just it's indirect. So what a random intercept does is, it goes into the linear predictor. So it indirectly creates a covariance between the occasions from the same person. Rather than just saying, just let it be in the model, it shows up indirectly through this addition as a random intercept at what looks like another predictor. It's a random effect rather than a fixed effect. So if we're in the world of general linear models, it doesn't matter which way you do it. You can have an R matrix and say that it's compound symmetry, or you can have this random intercept and an R matrix that is diagonal, that looks like this, where you're saying, once I control for the person dependency, the E's that are left have constant variance across outcomes and no covariance. That would be the V matrix that results from combining these things back together again is what's known as a marginal characterization of the outcome. And you can also phrase it as a conditional, where you move the random effects into the linear predictor part, and you're saying R describes what's left after you factor in the fixed and random effects. And so this is the notation we've been using all semester, this idea of a conditional distribution. And the reason for that is that what we're going to try and do is use random intercepts so that the conditional distribution is the same as what it would be if we were in a univariate model. Meaning all of the dependency, that the same outcomes, the outcomes that come from the same person, has been captured by the random effects. That way your E's or whatever you would have that would normally be there in a variance model are independent. So this latter effect, this conditional distribution, this is the only way within true maximum likelihood to fit a multivariate model that has generalized linear models within it. Because if you don't have residual variance, you don't have an R matrix. So we're saying like R right here looks like this because this would be normal. But R could also be Bernoulli. It could be multinomial. It could have whatever characteristics it needs. that don't necessarily include estimated variances. So this idea here, that we move the dependency out of R and put it into the linear predictor as random effects. We have to do it in order to allow dependency in models where residual variance is not a separately estimated parameter, which is the case in almost every other distribution except for normal. So you will see this in both multivariate models in univariate software as well as in path models. In path analysis, for instance, if you want to allow two outcomes to correlate, you can fit a covariance between them. It looks like a double-headed arrow in the notation. You can't do that if your outcomes aren't normal. It won't even allow you. So a random effect that predicts both of them is the workaround that it will allow you to do. The other downside to trying to fit these multivariate generalized models in univariate software is that it doesn't fit separate stretchy factors for each outcome. It doesn't fit separate thresholds for each outcome either. So the end result is that we have to use random intercepts to predict a correlation between outcomes from the same person, but what the conditional distributions can look like are heavily constrained in univariate software. It's very tricky to get it to tell, for this outcome I want it to be Bernoulli, and this outcome I want it to be count, and for this outcome I want it to be count, but I want to have a different stretchy factor. The limitation isn't in the modeling, it's in the software. Estimation also gets a lot harder when you have random effects in the model as well. The multivariate normal estimation basis that goes really fast and easy doesn't exist when you have generalized models. So I wanted to say a little bit about that because what you're going to find is that these models take longer to estimate. They're more likely to break down because estimation is not as easy when you are not in normal models. When you combine random effects with some kind of generalized non-normal conditional distribution, that's where the problem comes in. Questions, thoughts? I'm just going to pause and refuel. So I know it's a lot of words. Big picture, random intercepts create correlations between outcomes. They create a constant correlation. But there really isn't we don't have other options available to us. Like we just sort of have to pretend that that's good enough in the world of generalized models. Random effects is the only way to go. In terms of estimation, so a little bit about this. If we have random intercepts that are supposed to have a normal distribution, and we have E's, which is the within-person residuals that are supposed to have a normal distribution, you can put the two normals back together again and make a multivariate normal. That's what your R matrix would have been, and that's what your V matrix is, and that's fine. That's a ready distribution. I've got a likelihood for it. It's no problem. The same is not true when you have a non-normal conditional distribution. So what is the model implied variance, for instance, if you have a random intercept and you have, say, two binary outcomes that are Bernoulli? Like, how do you put a normal variable and add it to a Bernoulli variable and make something? The answer is you don't. Although in previous classes, people have tried to name such a situation. They came up with normuli or Bernormal as a new distribution that you could make. If you have a normal random intercept combined with Bernoulli original outcomes, conditional distributions, you could have a normuli or a Bernormal. Unfortunately, that is not a thing. There is no closed form, ready to go log likelihood formula that you can use for such a situation. And the same is true for any conditional distribution that's not normal. If you have a random intercept that's normal with a count distribution or a random intercept with a binomial, like those are not things that you can just put back together again. What you end up having to do is separate out the U's and their variance and then try to figure out what the rest of the model needs to have. There are three main ways of doing estimation in these cases. There's quasi-likelihood, there's numeric integration, and there's Bayesian methods. I wanted to point out, so quasi-likelihood or pseudo-likelihood. If you hear those words like it's quasi-correct or pseudo-correct, does that inspire confidence? No, ish, right? That those words mean ish. Like it works ish. It's correct ish. Yeah. Um, those approaches are much faster. They were developed earlier. They are approximations that try to pretend it's a linear model. And they have been shown not to work as well as other approaches that I want to tell you about. They are the default, though, in certain software packages. So for instance, that's the default in SAS Glimix. When you have random effects and a non-normal conditional distribution, it defaults to a quasi-likelihood. As near as I can tell, and I believe this is still true, SPSS only has quasi-estimation. So I quit teaching stuff in SPSS a long time ago because of that, and they haven't kept up. You will have to look into your software package to see what it is doing. Because if you use these quasi-estimators, those log likelihoods that you get are not true log likelihoods. You cannot compare them. You cannot use them to do log likelihood or log likelihood ratio tests or anything like that, which is the primary way that people test whether random effects belong in the model. So they're limited in that set. The thing that is, I would say, to look for, these are all words that you should look for in your software manuals to figure out what they're doing. Numeric integration. Sometimes it's called numerical integration. It's sometimes called Gaussian quadrature. That's another one. Any combination of those words means that what it's doing is a true maximum likelihood process. It is a maximum likelihood version. There is no residual maximum likelihood. Residual maximum likelihood is only possible for normal conditional models. It does provide valid log likelihoods that you can use to do model comparisons. There is a sort of computational shortcut version that you will see called Laplace. That word shows up in the context of models that have crossed random effects or sometimes that have more than two levels of analysis. So there'd be two different sets of random intercepts, for instance, in a three-level model. The way that it works is by trying to get rid of all of the U's and then figure out what the rest of the model would look like. So it starts with whatever values that you might try out for the fixed effects. You can get them from the data. You can use calculus to figure out which way they should go next. It computes the log likelihood for each observation given the current parameters by trying on possible values of the U's of what they could be, and then weighting the result based on how likely the U's themselves are. So the idea of this is that if our random intercepts, so each person has their own random intercept, but it's an error type variable, we don't know what it is. We have to allow the model to try out possible values of these random intercepts. And so this picture right here gives you sort of an approximation of what is known by quadrature. It's rectangling a distribution. So it's a way to approximate area under the curve. It's in a discrete fashion. So adaptive Gaussian quadrature, which is what this is called. Gaussian means that we're assuming that the random intercept has a normal distribution. You have to assume that, by the way. The software won't let you get around that for the most part. And the number of rectangles that you're using to try and divide up this distribution into possible values, that's known as the number of quadrature points. That's also something else that your software will tell you in the documentation what it's doing. SAS, for instance, when you say that you want to use numeric integration and quadrature points, it figures out how many it thinks it needs. So it makes that decision for you. Stata has 7. Why 7? I don't know. It just does. M plus 15. It just does. So in my examples, you will see me sometimes set the number of quadrature points to be equal to a certain value, just so I can get the program's output to agree, not because that value is necessarily the best choice. In practice, more quadrature points is better up to a point. And so that's why the program in SAS picks how many it thinks it needs. The more you have, the longer it's going to take. So 15 is standard, like I said, 7, whatever it is. That's the number of tries for each person's U that this is going to go through. So let me try to explain this a little bit more concretely, because this was a table that I've adapted from another book that actually was the first time I felt like I understood this. So let's say that I have a model that has 2 binary outcomes, okay? I need to put in a random intercept so that there is a correlation between my 2 binary outcomes. After controlling for that random intercept, which is supposed to capture the person dependency, then the resulting distribution is Bernoulli. So I have a normal random intercept with 2 Bernoullis. And they're independent because the random intercept is the thing that was supposed to capture the correlation between the 2 of them. So let's say that I have a fixed intercept of 0.5 as my fixed effect try-on guess during this round of iterations. And I have a slope for a predictor of 1.5. So I have a dummy code that says which Bernoulli outcome it is, 0 or 1, and the mean logit mean difference between the 2 of them would be 1.5. Doesn't matter what the numbers are, I just need some numbers to go through the table. So let's say that we're going to try on 3 quadrature points. I'm going to pick 3 values of a random intercept to try on and figure out what the model predicts my logit to be and compare that to what the actual value was. So let's say that I pretend that I'm dealing with a standard normal distribution, just for numbers that work well. And I'm going to try on a U of -2, a U of 0, and a U of 2. And here's my model. So for this person right here, this person has a 1 for both of their outcomes. Okay, we know that much in the data. So if it's the reference outcome, and I try on a U of -2, the model gives me an intercept of 0.5, the slope drops out, 0.5 minus 2 gives me a predicted logit of -1.5. So the probability of getting a 1, if I unlogit that back down to probability, that logit of -1.5 translates into a 0.18 probability. That's what it is if they were 1. For the other outcome, the model says it's the intercept plus the slope minus my random intercept of -2. That gives me a logit of 0, which converts into a probability of 0.5. If my random intercept is successful in capturing all of the correlation between these 2 outcomes, which it has to be by definition for just 2, then I can multiply my 2 outcomes together because they're supposed to be independent. So I have my probability of a 1 for this outcome and for that one multiplied together because that's what I know I got. That's my likelihood. I do the same thing here by trying on a U of 0. So my model says that my predicted outcome would be this. That translates into this logits, which translates into this probability. Multiply those together, I get this one. Now if I try on a, damn it, I keep finding errors in these things because I use the same table for both classes. It's not theta, it's random intercept of +2. That translates into a logit of 2.5 or 3.5. Those probabilities multiplied together. So it's like, okay, if my random intercept was this, these are my predicted probabilities of what happened. If my random intercept was that, here's my predicted probabilities. Well, I want to find some way of combining all of those back across all the possible values of U that I tried on. but I don't want to weight them equally. I want to weight the u's based on how likely they are, given a normal distribution. And so that's where the areas come in here. A u of -2 is very unlikely. A u of 2 is very unlikely. The most likely is the u of 0. So we downweight each of these as a function of how likely the u's are. We end up with these final numbers, and if you add them together, add them together because we're rectangling and adding, that is integrating basically the area under the curve where the thetas are, and we end up with this number. And so every single time you try out new possible values in the likelihood where it's searching for what makes everything the tallest, you have to go through this try-on process. So it's integrating the random intercept out of the likelihood by trying on all possible values and combining what the result is weighted by how likely each random intercept would be. The more quadrature points you have, the more try-ons you have to have. If you have more than one intercept or more than one random effect more generally, it would be 2 to the power of quadrature points. So if I had 2 random effects and each had 7 quadrature points, like in Stata, that's 49 try-ons across the 2. So the analysis estimation process takes a lot longer and can get bogged down because of this try-on process. So you may have to wait a little bit for these things to converge, and sometimes they may not. So yeah, that's what I want to say about that. Estimation is hard. So I'm guessing that some of you are like, oh my God, please stop talking about estimation. I'm going to cry my eyes out. That's fine if you're in that camp, because so am I, to be honest. This is not why I get up in the morning. But there are some of you who are like, oh, this sounds really cool. I wish I knew more about it. Can I get a yellow thumbs up for anybody in the second group? This is really cool. I wish I knew more about it. Any yellow thumbs ups? There's one. I got one. Well, for those of you, I would like to, oh, there's two, Kelly. All right. Jing, you better get your thumb up. I can see you. You're in the quant program. You have to pretend to care about this. But for those of you who care or must pretend to care, I'd like to pimp my husband's class in the fall. He is teaching a new seminar on estimation methods, where he will go over some of this stuff and including Bayesian versions in more detail so that you can get a better sense rather than my hand waving about how all of this works. So this is not my area of strength. But bottom line, generalized multivariate models are harder to estimate and take longer. Can we just agree on that? That's your take-home message, okay? Because you have to integrate the U's out. That's just what's going to happen. Here's a thing I put together to try and let you know what is possible in the software that you know already in terms of what you can do. There in SAS, there's a BIOBS option that allows you to specify different link functions and distributions per outcome variable. It doesn't include multinomial. Hurdle models would fall into this category. Hurdles are when you have a count outcome that has lots of zeros, and you can separate out predicting whether or not someone is a zero versus how much they are if not zero. Those are called hurdles, or if and how much more generally. You can do some of that in software, but much less in SAS than in Stata. Stata doesn't have multivariate versions of these models, though, as near as I can tell. And then in the path model stuff that we're heading, these are the choices that we have for generalized multivariate models, M+ and Stata. These are the ones that I'm going to show you because they have the most options relative to other things that I've seen. So let me show you, this is my wrap-up thing. One more piece where you specify this in the software. In example 5, how you get a random intercept in the model. Find this. The very last thing that we did was trying to fit this as a multinomial ordinal model. Let me find that real quick. Almost there. It was model 6. One more. There it is. Nope, I cheated. That's right. Never mind. I thought I had tried to do both outcomes in the same model with the random intercept, and now I remember that I didn't because I couldn't get different thresholds across, and so I just predicted the different score. That's right. Never mind. I had good intentions, but it didn't work. Yeah, that worked. Pancakes and crepes worked. Okay. Anywho, yeah. So we're ready to start path models next time. That means I need to get that lecture done. It's not done yet, so I will work my best on getting that done in the next day or two. In the meantime, let me know if you have questions on homework or otherwise. I think that's all I want to say about that. Do you have any questions from today? Nope. Okay, so big picture, make sure we're following here. When your outcomes have normal residuals and you want to predict more than one outcome at a time, you can just tell it, let my residuals be correlated in the R matrix, and they are. Cool. And that works because each outcome has an estimated residual variance. When each outcome does not have an estimated residual variance, which is true in every other family, you can't have residual covariances either. But we still have to have the residuals be correlated. So the way that it works is by trying to take the total variation in the outcome and say that some of it is because of this constant person dependency, this random intercept thing that's normally distributed, and then what's left is Bernoulli or binomial or Poisson or whatever. So random intercepts are a hack. They are a way to get back to a conditional distribution that assumes independence, because any of the dependence is supposed to have been captured by the random intercept that goes into the linear predictor as a random effective person, essentially, that goes with the fixed effects. Okay, that's my big picture. Does that make better sense? Okay, fair enough. It's complicated. I mean, it's not one of those things you understand immediately, and I'm still working through it, to be honest, and the notation especially. But the random effects are a way to induce correlation between outcomes when you can't put it in there directly. That's my take-home message. All right. Anything else before we adjourn? All right, then I'm going to turn on office hours and get to work on my lecture for Thursday. And if I can't get it done, we may just have extra time for homework. Would that be okay? Would you guys prefer that? I'm not lying. You can say yes, because that would actually make my life easier this week to not have to finish a lecture in 2 days. Chat window says, where did my chat window go? I lost it. There it is. Yes, Kelly says. Okay, we take a vote. All for extra time to do homework and ask questions instead of starting a new topic, raise your yellow hand or your real one. Oh, it's almost unanimous. Okay. Then thank you, guys. That's what we'll do. Oh, I appreciate that. Yes. It's very hard to work under pressure. And that's all that we have right now. Thank you. I will work on getting my lecture ready for next week then, and then I will have class time just as open time for homework type questions then. So you don't actually have to come unless you want to sit here and work on it and get help as you get stuck. How's that sound? Okay, that's my new plan. I will send out a new email letting other people know who are